The frog hopper, a tiny insect, is a remarkable jumper. Suppose you raised a colony of the little critters on the moon, where the acceleration due to gravity is only 1.62 meters per second square. If on Earth, a frog hopper's maximum jump height is h and the maximum horizontal range is r, what would its maximum height and range be on the moon in terms of h and r? Assume a frog hopper's takeoff speed is the same on the moon and on the Earth. Now let's organize our knowns and don't knowns in one table. So it says the acceleration due to gravity on the moon is 1.6 meters per second square. Let's write that in here. G on the moon equals 1.62 meters per second square. Maybe it's important for us to also write G on the Earth equals 9.8 meters per second squared. And then it says on the Earth, maximum height, so I'm going to call it H max, equals H, and the maximum horizontal range on Earth equals R. So I'm going to take the subscript of maximum and put the H Earth in here. It says what would be the maximum height and range on the moon. So what we're looking for the maximum height on the moon and maximum range on the moon in terms of H and R. Also, it says the takeoff speed is the same on the moon and on the Earth. So V on the moon equals V on the Earth. Let's start from the first part when we're solving for maximum height. So for that, let's picture the situation. Suppose this is the ground and the grasshopper is going to do the motion of trajectory, go to the to the highest peak and then go down and hit the ground again. So in this case, we have a maximum height in here. And one thing that we know about maximum height, that the Vy equals 0. So in this situation, we have an initial position at this point where x equals 0, y equals 0. Well, we're talking about initial. X initial, y initial equals 0. And then we have the velocity at a certain angle, initial velocity going this way. At a certain angle, let's call this theta. And then we know that the final position for the grasshopper at the highest point would be H max. Let's say either on the Earth or on the moon. It doesn't at this moment. Let's just call it on the Earth, things on the Earth. And X we don't know, and we don't really care about it at this point. Obviously, I have set my coordinate systems, positive X going to the right, positive Y going upwards. So we have to consider that our accelerations are actually negative and consider that in our calculations. Now, it seems like to find the h, we need to find the delta y for the Earth. So let's write for the Earth, we would have delta y on Earth equals y final minus y initial, which is h on Earth, minus 0, and that equals h on Earth, which equals h. Well, similarly, we can write for the Moon. Delta y on the Moon equals y minus y naught on the Moon. That equals h on the Moon minus 0, and that equals h on the Moon. Now, let's use the equation that we have, the fourth equation, since we don't have time and that's only equation we have that doesn't involve time. I can write Vy on Earth squared equals V naught y on Earth squared plus 2a on Earth, acceleration on Earth, delta y on Earth. So we have final velocity at the maximum height is 0. So I can say 0 equals V naught y. I'm going to skip the e for V naught because they're equal to each other. Squared plus 2ay h. So from here, I can say, I can solve for h. H equals V naught y squared over 2ay, and let's not forget our negative in here. Now let's do the same thing for the Moon. Exactly the same reasoning will give us a result for the maximum height on the Moon. So Vy on the Moon squared equals V naught y on the Moon squared plus 2a on the Moon and delta y on the Moon. So we get, again, it's a maximum height, so the Vy is 0, so we have a 0 equals V naught y squared. I'm skipping the subscript Moon because we know V on the Moon and velocity on the Earth are equal to each other, plus 2a on the Moon, delta y on the Moon. There is one little thing that you might disagree with me, where it says assume Froghopper's takeoff speed is the same. Although it says speed, I honestly think this is a mistake in the problem. It actually needs to be velocity, which means the angle theta on the Moon and on the Earth are also the same. So pretty much we should put the vector sign in here, which means the theta is also the same. Now let's go back and find delta y on the Moon. Actually, let's substitute delta y on the Moon with the h Moon and solve for h Moon here. That equals negative v naught y squared over 2a moon. Now, if we take and divide this equation 1 and equation 2, I would say hm over h, the left side you divide by each other, the right side by each other, you'll get negative v naught y squared over 2a on the moon over negative v naught y squared over 2a on the earth. So I think I need to make a little correction here. I wrote it wrong, so this should be earth, a earth, although ay is also correct. Now this will cancel out, the negatives will go away, the 2 will cancel out, we'll end up having equals a on earth divided by a on the moon, which is negative 9.8 meters per second squared divided by 1.62 meters per second square, and this should give us 6.05. So I can find the h on the moon equals 6.05 times h on the earth, 6 times higher. Now let's solve this problem now for range. You should understand that this problem involves kind of 2 small problems in it. It's kind of complex, and it requires separate approaches from each other. So now let's do a range. Let's understand how the grasshopper's trajectory happens. So grasshopper starts from initial position where x initial equals 0, y initial equals 0, and then we have a velocity initial here. And then what happens, it's going to jump up to the maximum height, jump down, and get to the ground again, where you have x final, y final, and v final, and we really don't care about this. One thing that we know, that the y equals 0 in here. So what we're looking for is the x, which will be the range. Now delta x on earth equals range on earth, and equals r, and delta y on earth equals 0, because initial and final positions are 0. Now let's see, delta x on earth equals v naught x times time on earth. The situation is the same on the moon, where you have a delta x on the moon equals range on the moon, and that's what we're looking for actually. And delta y on the moon is going to be 0, because the projectile motion is the same. So, and delta x on the moon should equal v naught x times time on the moon. So the only difference is the time. We already know that initial velocity is the same. Now let's put here rm, and here we'll just put an r, because that's what we will need. Now we can't do much unless we find the time on the moon and time on the earth. Once we find it, what we could do, we could divide the range on the moon, over range on the earth, that equals v naught x times t on the moon over time v naught x time on the earth. This will cancel out. From here, I can find range on the moon equals time on the moon over time on the earth times the range on the earth. Now, my goal is to find time on the moon over time on the earth. So for that reason, I'm going to go to y component of this motion. Let's start with the earth. I can say delta y on the earth that equals to 0 equals v naught y t on the earth plus 1/2 a y. Actually, let's put a on the earth. We already know it's the y. T earth squared. I used the third equation here. And then from here, I can bring this term to the left. That would be -1 over 2 ay earth t earth squared equals v naught y t earth. So one of these t's will cancel out. Then we'll find t on the earth equals -2 v naught y over a y on the earth. We can do the same thing for the motion on the moon, which we can write delta y on the moon equals v naught y t on the moon plus 1/2 a y on the moon t on the moon squared. So making the same analysis, we could write 1 over 2 ay on the moon t moon squared equals v naught y t moon. So again, one of the t's will cancel out. We will have t on the moon equals -2 v naught y divided by a y on the moon. Now let's plug in our values for t on the earth and t of the moon in our expression. That will give us, okay, so t on the moon is -2 v naught y over a y on the moon, and then te is -2 v naught y over a y on the earth. This will cancel out. We'll get a y on the earth over a y on the moon. And of course, I forgot the r here, times r. If we plug in the values, -9.8 meters per second squared divided by -1.62 meters per second squared, r will give us 6.05 r. So the range is going to be 6.05 times greater on the moon than it is on the earth. So if you land on the moon and you want to move a distance by jumping, it will be much easier and faster, and you will feel way lighter. Thanks for watching. Stay tuned for more to come.